Memory footprint is the amount of RAM that a program uses or references while running. My name is Liviu Esanu, and today I will be talking to you about memory footprints in Golang. Welcome to my talk. Now, I work at Metronome as a Golang developer. Metronome is a large company. It has large systems built by large teams. Through the years, this has given me an opportunity to see how they behave, how large-scale systems work, what problems could sometimes appear. And, of course, it has also given me the opportunity to learn a lot about memory. I will be sharing with you some of my learnings. We will go together through some memory connected issues. Thank you for joining me. Please be warned, they are in ascending order of difficulty. Okay, why do we care about memory? Why does memory knowledge matter? What can it do for us? It's pretty much about saving CPU and RAM. We know the inner workings of our language. We know the inner workings of our system. We can apply tricks, best practices, to maybe squeeze out a little bit of CPU, a little bit memory here and there in a few spots. This comes, however, with some trade-offs. I'm talking, of course, about readability, maintainability. So the things you are about to see, you are personally responsible for choosing when do you apply them and when not. Let's get to it. On the line of code behind me, I declare a global variable g. Its type is a slice of int32. I want to find out, during the time my program runs, how much memory will my variable consume. What's the behavior memory related of my variable? How can I do that? It's not really that easy, but my first bet, the first options that I have, is calling the unsafe method. Calling the unsafe size of method. So this size of method will tell me basically how many bytes my variable will occupy. Of course, what it does not do is, if my variable has a pointer field, it will not follow that pointer, see what it points to, compute how much memory that thing also consumes, scan through that, are there pointers over there, and follow them as well. No. Size of simply iterates through the fields. If it's a pointer, it's going to be 8 bytes and so on. A much better approach is creating a benchmark. So on the screen, we can see the following code. Line 1 through 3 is the getSlice method. This method returns a slice. On line 4, we have a global variable. And line 5 through 9 is our actual benchmark function. What does the benchmark function do? On line 6, we see that it runs a for loop. Inside the for loop, it calls my getSlice method. The for loop will run b.n times on line 6. Now, this b.n is automatically adjusted so that my benchmark method runs for about 1 second. During that run, some statistical data is collected about it. At the end, after running it, I can display that data. Here's how I can run the benchmark method, the code you see. Notice the flag benchmem. Setting this flag as well will show me how much memory on average each iteration of the for loop consumed. This is good for us because it's precisely how much memory our getSlice method used. So, having these two options, let's look at their results. So, here are some common data types used in Golang. Notice that for the builder, from the strings package, both size of and the benchmark produce the same result, 32 bytes. For the rest of them, size of produces a much less number of bytes. Okay. Why is this? It's normal. It does not follow pointers. It does not do thorough scanning. But I hope that this intuitively tells us our data types, our objects, they're not just pieces of memory where we store data. They are pretty complex animals. They have overhead fields. They have hidden pointers. we need to think them in a more complex manner. It's not just a place where we store data. Let's take a look now at how some commonly used data types in Golang, how they look like inside. What do they contain? Whenever we use a slice, this is what actually gets created. Note the slice structure. 3 fields. I have run this code on my laptop. It's a 64-bit machine, Golang 12. So an int will be 8 bytes here. These 3 fields, all of them will take 8 bytes each for a total of 24. I want you to notice something about slice. The useful data, the payload, the stuff that I want to store in the slice. It is not found in this structure. Notice that the useful stuff is found on line 2. We have a pointer. This pointer is to the location where my data is actually stored. All these 3 fields are overhead. They are needed for my slice to run as needed, of course, but they don't really store my data. For a small slice with just one element, it could be that this overhead is larger than my element, of course. When I have lots of elements, overhead is negligible for slices. A more memory efficient, from my perspective, data structure is the time from the time package. Please note the 3 fields. The 2 fields, the integers, both of them hold time information. The third one is a pointer to a location object. With this data structure, I would say that I have 2 payload fields and 1 overhead field. So it's pretty efficient. A more complex data type, the map. What's going on with the map? It's a type specific to the Golang language, of course, and anytime I use map in my code, anytime I write code using a map data structure, at compile time, the compiler will replace my code with calls to the runtime package. In memory, when I use a map, this is what gets created. Please note a large structure with lots of fields. And when I mean this is what gets created, I mean this, but also some other additional useful. It's not the only one. Let's take a look at what it contains. Where shall we start? Well, most importantly is line 7. It's a pointer to the location of the buckets. We all know that in a map I can store key-value pairs. This data is stored in something called buckets. These buckets, of course, occupy memory. They are at some memory location. Here on line 7, we have a pointer to them. On line 8, we have another pointer to the old buckets array. We know that maps do resizing. They have automated resizing functionality. The number of buckets doubles. The values are being copied in the new bucket array. So this pointer is also needed. The rest, so basically everything in this HMAP structure is kind of overhead. Like I don't really store data here. I store data in the buckets. The last data structure that I want to show you is the channel. Again, whenever I use a channel in my Golang application, at compile time, the compiler replaces my code with calls to the runtime package. This is what gets created in memory. Now, a lot of fields. Please notice line 4, it's a buffer. Now, if we have a buffer channel, let's say it's a buffer channel of capacity 5, it needs to be able to store 5 elements inside it. This is the buffer where that storage is done. Line 10 and line 11, we know that Go routines wait to read to a channel, wait to write to it. So they are stuck. Channels are used not so much for data storage, but for synchronization. These are the queues. Line 10 and line 11, the receiver and the sender queue. Here, each Go routine that is waiting for this channel will have something representing it. Again, payload to headers, we see that, I suppose the buffer and the waiting Go routines, these are useful payload, the rest is headers. Okay, Let's imagine the following situation. We have a large library and we have a collection of books. We want to place the books in our library. We place them on the shelves, of course. We go through most of the books and there's one book left. For this one last book left, we have option A, figure out a way in our library to place it. Okay, get creative. Option B is get a bigger building. Intuitively, option B, we can see that somehow the cost of getting a bigger, larger building is going to massively overwhelm the cost of my last book that I do not have place to store it. That's why option B is not really used in real life. But in Golang, we have a similar situation. We know that the slice data type has automatic resizing mechanisms. So let's say we have a slice, we have a capacity, we have added elements to it, its capacity is full, and we want to add another element. We append it, what happens? A new memory gets allocated, the old elements get copied to that new memory, plus the last element that we appended. The result looks something like this. We have a large portion of memory, its first part is being used, the last one is still being used, it's occupied, but does not hold any payload, any useful information. Okay, for small slices, this is not important. We can get by just fine. For large slices, this is something we try to avoid. Imagine something like having a 1 GB slice. We append one more byte to it, one more element. It's going to resize. If its capacity is full, it's going to resize to something larger. It's wasteful from a memory perspective. This is why if we happen to know from the start, from writing the code, what's going to be the maximum capacity of my slice, I allocate it from the start with whatever I'm going to need to use and not more. If, however, I'm not that lucky, I'm not going to know what's going to be at runtime, the maximum capacity that this slide will hold, I need to come up with some other alternatives. To do that, it would help me if I understand this resizing mechanism a bit better. So, we know that slices resize. What I've done here is I took all the values from 1 to 50,000. I created a slice of that capacity, appended one extra element to it. The slice got resized. And I divided its new size to the old size to figure out this resizing factor. The results are in the graph behind me. Please note that for capacities up to about 1,000, when resizing, the slice gets kind of double. 200 to 150% is the resize factor. If my slice is between 1,000 and 3,000, the resize factor is going to be something like 135%, somewhere over there. For largest slice capacities, the resize factor goes to 125. This is how Golang works. Other programming languages have a constant resize factor. It's always doubling. Remember the array list from Java? It's always doubling. The slice in Golang does not double. For large values, is getting 25% more. Now, do note in this graph there are a lot of zigzag lines. They are not a mistake. What do they represent? It basically goes like this. Imagine we have a slice of capacity 10,000. Append one element to it, it gets resized to some new capacity x. Then, a slice of capacity 10,001, 10,002, and so forth. When they get resized, they will be resized to that same x. For intervals of about 800 values, it's the same capacity that they resize to. The code is very fascinating. Do look through the implementation. It's done for optimization reasons. And it's pretty hard to tell in words a simple resizing factor rule. The best way I could come up with is this graph. Slice is not the only thing that gets automatically resized. The map data structure as well has a resize functionality. So, what's happening in Golang? Map stores key value pairs. We know that these key value pairs are stored in something called buckets. A bucket can hold up to 8 such key value pairs elements. Of course, when a bucket is full, when a bucket has 8 elements, and we want to append another element to that bucket, a new bucket gets created, it gets chained to the already filled one, and our element is stored there. The Golang implementation of a map is a hash map. So for each element, the hash code is computed. Based on that number, it decides which bucket it belongs to. Good. Golang maps have a load factor of 6.5. What does this mean? If, on average, every bucket has about 6.5 elements, it will get resized. Notice in the image behind me, this map has about 6.5 elements on average in each bucket. It is about to resize, and we're going to watch it. What happens when resizing? The number of buckets doubles. We have doubled the buckets now. Every element is placed into these new buckets. Of course, hash codes need to be computed and so on. But I want you all to notice and remember this about the map data structure. The memory used by this structure is going to be used to store our values. That's useful payload. Buckets also need memory. They are objects. How many buckets we have? Well, on average, we have at least one bucket for every 6.5 key value elements. This means that, due to this resizing thing, the memory consumed by the overhead, the memory consumed by these bucket objects, grows linearly with my payload. This is why maps have fast insert, fast retrieval time, but they consume a lot of memory. We pay for speed with memory, whenever we use a map, in Golang at least. Reality does not always match expectations. We talk about some language-specific data types. Let's also take a look at what happens with our custom-defined structures. I'm allowed to define structures. I do this all day. What goes on with them? The way Golang is built is that it supports this address alignment guarantee rule. Namely, for every type T, there's this guarantee, address alignment guarantee number, n. The rule says something like, every value of that type at runtime, its address must be divisible by n, must be a multiple of n. Pretty theoretical, pretty abstract rule. What does it mean for us in our day-to-day work? Before getting to some examples, let's take a look at some address alignment guarantee values. We see that for small data types, it's like for numerical data types, it's 1. For larger-ish, like complex 64, it's going to be a 4. For structures, slices, and more complex, it depends on what you store in them. It depends on the fields they contain. Look at this piece of code. It's a structure. It has two fields, a byte field and a slice field. The slice is a slice of byte. I want to know how much memory will an object of this structure will consume. I already know that a slice of bytes is about 24 bytes overhead. If I print how much memory is being used and how those fields are displayed in memory, I come up with this result. So my structure will be 32 bytes. What's going to happen is that the first byte holds my byte field, then 7 empty bytes, then the slice field. Why is this? The slice field has an address alignment guarantee of 8. Its address must be a multiple of 8. So I need to have 8 bytes before it, if it's the second field. That is why my structure consumes a little bit more memory than I would like it to consume. We have a second example. Very similar structure. This one has more useful byte fields. It has 3 of them. I want to know how much memory it will consume. In a similar way, the first 3 bytes will be consumed by our 3 fields. Then 5 bytes of padding, empty space, then our slice field. There's a lot of workaround. I advise you that when actually designing custom structure, do change the order of the fields, do change the type of the fields. You can squeeze and save a little bit of memory this way. If you want to take it a step further, what happens with our map data structure? We know that it stores key value pairs in something called buckets. How does a bucket look like? Well, it's pretty interesting. They made the decision to store both keys and values in the same byte array. We know that a bucket can store maximum 8 such key value pairs. We know the size of each key and each value, so we know how many bytes this array will take. This decision was done for caching reasons. Anyway, once they did this decision, they stored the keys something like, first we have the 8 keys, then we have the 8 values. For a map bucket that's not full, it has like 5 keys, empty space for the rest of the keys, then the values. Why is this? Why didn't they just store key value, and so on? If they were to have stored key value in the same byte array, it would have been address alignment guarantee issue. Depending on the type of the key and the value, some extra padding, some extra empty space could have been added between them, and they just chose to be very memory efficient. Now let's talk a little bit about the heap and the stack. Well, we know that every Golang program, its memory is split in 2 parts, the heap and the stack. What does it mean? Well, we have 1 stack per Go routine, and we have a single heap. The heap can be accessed by all Go routines. Objects, as I need to allocate them, will go either on stacks and on heaps, or in the heap. What is important, what I want you to remember, allocating on stack is much faster than on heap, and only the heap gets garbage collected. The stack obviously does not need to be garbage collected. Okay, this is all nice and well, but what does it mean for us? How do we know when an object will be placed on the stack or on the heap? The compiler does something called escape analysis. This happens at compile time. For every object, it goes through a list of rules. The list is pretty large and complex. I'll just name one. For example, if the field of a structure goes on the heap, then that whole structure will be allocated there. Now, escape analysis, the compiler goes through these rules and decides for each object where it will place it, heap or stack. Let's take a closer look at the heap. Well, it's a piece of memory. Every Go routine can allocate there. Okay. What happens in Golang is that there is a size segregated heap model. Namely, there are multiple heaps. There's a heap for storing elements of 8 bytes. There's another heap for storing objects of 16 bytes, and so on. So all objects of the same size get to that same heap. With one single point to notice, every object, when decided to be allocated on the heap, its size will be rounded up to the smallest heap that can accommodate it, and it will be placed there. Here's a graph with some of the heap sizes. For small elements, the difference between 2 consecutive heap sizes is like 8 bytes. For larger one, the difference is increasing. These are not all the heap sizes. The largest 2 of them, there's a difference between them of about 1,500 bytes. Okay, good. What does this mean for us? Well, let's take a look at the code on the screen. We have a get channel method on the first 3 lines, and from line 5 through 9, we have a benchmark. What will the benchmark show us? It will show us how much memory our buffer channel will occupy. Please note that the method creates a buffer channel of size 100, of capacity 100. Now, my question is, how much memory will this buffer channel actually occupy? If I am to look at an unbuffered channel, it's going to be 96 bytes. I could mistakenly assume that for a given channel, its actual size will be this 96 plus the memory size of one element, in case if it's an int, the size of an int, times its capacity. This is not exactly true. I've run the code. For small values, it's pretty close. What happens is this gets allocated on a heap. The size of my channel gets rounded up to the smallest heap that can hold it. And we have, for a channel of capacity 1, 112 bytes, and so on. For larger capacities, it gets even worse. Please notice here, if I have a channel of capacity 100, 896 bytes, it's okay. If my capacity is 101, then it will be rounded up to the smallest heap, The smallest heap is 1024 bytes. Let's move along to the next part of our talk, the garbage collector. We all know Golang has a garbage collector. Golang is part of the garbage collection programming languages. It's a very efficient garbage collector. Golang has a concurrent one, namely it does not stop the program, freeze the program, do garbage collection work as it happens in other languages. What it does is it's a concurrent one, namely when a new garbage collection cycle is running, if a Go routine wants to allocate memory, this Go routine, if it wants to allocate more than it freed in the past, so it's in allocation debt, this Go routine will be forced to do some garbage collection work. It does not freeze the program for a little bit, but it slows the program for a little bit. This could be seen maybe in REST APIs. If you have a very large heap, you notice the calls are less responsive. Yeah. It is also a mark and sweep garbage collector. What does it mean? The mark step is it scans through the heap, it looks for pointers. Every object that has nothing pointing to it is free to be garbage collected. And the sweep phase, it tells the operating system, please free this memory. Now, sweeping takes the scanning for pointers. This is what takes the bulk of the garbage collection work. Marking is slow, sweeping is fast. Sweeping, freeing elements fast. Scanning for pointers, this takes the work. Why? Because we have large heaps and you need to go through all the pointers, every single garbage collection cycle. We can tweak around a little bit with the frequency of when we run such garbage collection cycles. Namely, we have this environment variable, GOGC. Its default value is 100. This means that when the size of my current heap is 100% more than what it was at the end of the last garbage collection cycle, I will start a new garbage collection cycle. What does this mean for us? How can we apply this knowledge into our code? And here's a list of tips. Tweaking the GOGC environment variable is nice, but there's an easier way to think about it. It's called the Ballast technique, namely, garbage collection cycles run every time our heap doubles. We want to save a little bit of CPU. We want to make this frequency, we want to make the garbage collector run less than it uses to. How do we achieve that? We can start our program with an already large heap. Notice in the code behind me, I want to start my program. It already has 1 GB of heap memory. Whenever that doubles, run a garbage collector cycle. Since the heap is already large, these cycles will be less often. Scanning for pointers. Scanning for pointers to determine which objects need to be garbage collected. Now, if an object has no pointers inside it, it will be scanned the first time. Then, in other garbage collection cycle, it will be left away. It already knows that this guy has no pointers. So if I manage to create my data types so as that they do not contain inner pointers, they will no longer be scanned by the garbage collector. This way I save CPU. How do I do that? How do I get my data types not to contain fields that are pointers or contain pointers themselves? Well, don't use pointers in your fields for such a data structure, and avoid using things that have hidden pointers like strings, slices, builder, time, and so on. Channels, maps, of course. I can go even a step further. I want to have as little pointers in my program as I can. We all know that strings do have a hidden pointer. Here's a fancy way, a tricky way to represent a string. Please be warned that this technique is, of course, not production code. When writing this at work, you could be asked, why are you doing this? It has a large hit in readability and maintainability. Anyways, we have our custom string structure, and we have this slice of bytes. What I want to do, I want to store strings And I want these strings to be stored in my slice of bytes. Their characters are in this centralized slice. I have two methods, the store method and the get method. I need to be able to both places, add a string to it and read from it. Okay, what does that help me with? It's not readable, it's not likely to be applied in production, but let's take a look at what it does memory-wise. In this code, I create 1 million strings. I have this slice, it has a capacity of 1 million, I put strings inside it. Then what I do is run the garbage collector and print how much did this garbage collection took. Then what I do is again run the garbage collector a second time and print again. I want to see any difference. Last line, line 12. It's runtime keep alive. I'm telling the garbage collector, do not garbage collect S, my slice. What will this produce? Well, I see that it takes about 22 milliseconds for a garbage collection cycle when I have these 1 million strings. This makes sense. It needs to scan through 1 million pointers. The alternative approach is use my custom string structure and my slice way of storing strings. I have a single slice, one pointer. I store 1 million strings inside it. Then I again run the garbage collector twice. I'm telling it, do not garbage collect my slices. And I obtain this. Now the garbage collection cycles run an order of magnitude less. Why do I print it twice? Why do I run it twice? Maybe when creating the string, some extra memory is being used. I want that cleaned. The second run of the garbage collector will tell me an estimate of how much time it needs to do all that scanning. Another tip is allocate on stack. Use the stack as much as possible. If I could put my data on the stack, it would be much faster memory-wise. Now, this is hard to do because escape analysis is a pretty complex subject. But one nice trick is this. Memory passed via an interface escapes on the heap. Calling things via an interface, they get on the heap. What I can do, avoid programming via an interface. Also, avoid using the print family of functions because they have a variable argument of type interface. Anything I print gets converted to an interface, thus will be allocated on the heap. Now, I have another example, the last tip that I want to show you. Before getting to the question, I guess maybe there's a minute to go to that one. After it, please join me at the booth, at the metronome booth, where I will be for the next couple of hours. And this is the most important tip that I want to give you. Namely, it's very simple. Develop the habit of memory profiling your code, the most important part of it, the critical part of it, the one that's going to be used the most, the bottlenecks. Having this habit will give you a lot of knowledge about memory. So, we have here a main function. Package main, our main function. Here, on these lines, we enable the CPU profiling. This is standard code. You can copy-paste it. We're not interested in it. Line 20 to 23 is my program. I have a slice of int. I append ints to it. OK. Below it, we enable memory profiling. So we enable CPU, then our code, then memory profiling. We don't care about how it's done. We tell the garbage collector not to collect my slice. And I want to see how much memory will this consume and how will it look like memory-wise. I run my program. Then I launch pprof. It tells me useful information about my memory usage. Now I can see here that 35 megabytes were used by the main method. Okay, let's take a closer look. It can show us line by line what happened. So I see here that on line 22, where I append to my slice, this thing took about 34 megabytes. And now I'm getting curious. Well, 1 millionth ints should be somewhere like less than 8 megabytes. Why is this 34 megabytes? It seems kind of much. Noticing this, I also noticed that, oh wait, I'm using a slice. I know what its max capacity will be, but I keep appending to it. This is not a best practice. I could change the code. My slice starts from the start with the maximum capacity. I stop appending to it. I do something like then I run my program. Then I take a look at the memory. And here, I see that my main function takes about 8.7 megabytes. I want to take a closer look. Notice line 27.6, about as much as I estimated it. So here's how I done a little bit of optimizing on the code. Thank you for listening to me. I would be glad if you join me at the booth as well. Are there any questions now? Sure.
Thank you very much. How does optimization of memory affect real-life applications you do every day?
A very good question. And I fear it is a long answer, but I'll keep it short. So optimization of memory is not done in a void. It's done in a particular situation. Namely, you don't start looking at code and optimizing for a reason. You detect bottlenecks, you detect maybe bugs or code that's behaving badly, and you look at that. You research that, you figure out what's happening there, you optimize only these specific small pieces of my application. It should not be done sparingly. It should not be done with every single piece of code. It should be done only when it's needed. This is because of the trade-offs. I want to be able to easily read my code. I want to be able, let's say a new colleague joins, to easily understand it. I cannot really do every time, everywhere, some fancy memory stuff as we have seen. That's the short version. Long version at the booth. Yeah. Any other questions?
Hi, thank you for your talk. I have a question to your interface on the heap slice. Do you mean an empty interface or all interfaces that I can...
In the escape analysis, there is a list of rules. One of the rules says memory passed via an interface. So I mean anything that gets converted to an interface, it's heap.
Thank you.
Any other questions?
Also, thank you for the talk. Do you do the same mechanisms and tools to investigate memory leaks?
Well, obviously, there's pprof. To be honest, in this example, I chose the short version. I chose this example to be short and the way to run pprof to be the easiest to explain. In my company, in my product, we use plenty of tools, a bit more advanced than that, but it's a project-dependent type of situation. The bottom line is you do not really need anything fancy if you have this habit of profiling. And the good news is once you have the habit, you kind of know a little bit of best practice. You kind of see with the naked eye lots of spots. Maybe without that habit, you could not have seen them before. Yeah. Any other question? Thank you again, and I am at the metronome booth in the next couple of hours.